Hi, everyone. Welcome to another Alaska Collaborative on Health and the Environment. This is our October webinar with Chris Sargent on the risks of mining to salmon and trout-bearing watersheds in the Pacific Northwest. So I'm your host, Nick Reardon, calling here from Alaska Community Action on Toxics office. We're in Anchorage, Alaska. And yeah, winter just arrived. So we got a few inches of snow last night. And so that made my walk into work all the more beautiful. For those of you new to these webinars, the name CHE Alaska, it stands for Alaska Collaborative on Health and Environment. So there's a CHE. CHE is a national organization, which I encourage you to check out. And CHE Alaska is one of several regional partners. So in our case, we focus our attention on the links between human health, environmental factors, particularly concerning to Alaskans and Arctic communities. So yeah, with that in mind, I'm always curious what environmental health issues and concerns are important to you, your family, your community. What would you like to learn more about, basically, and what you think deserves additional attention? I'll pop my contact details into the chat box. And I also encourage you just to have a look. We have over a decade of recordings and even more than a decade of topics we've covered. So from previous presentations, and you can see info on upcoming topics on our website. So great for brainstorming and doing a little research. I'll pop those websites into the chat box as well, so you can have a look at your convenience. So, all right, moving on to today's guest and topic. We are very grateful to be joined by Chris Sargent, who has been working as a research scientist with a focus on freshwater ecology, as well as long-term monitoring, salmon biology, and in particular, the impacts of mining. So Chris has extensive experience studying emerging pressures on freshwater ecosystems, such as mining. Yeah, I understand has worked for quite a few years in southeastern Alaska, based in Juneau. So today's topic, Chris is the lead author on a recently published report summarizing the types of mining and the character of watersheds in the Pacific Northwest, and really highlighting how mining affects our region's salmon and trout bearing, or salmon and trout, these fisheries and these ecosystems. So the research findings, I will just give you a little snapshot before I pass over the mic, but they describe the stages of the permitting process and mine development, where potential mining-related harms can be identified and mitigated, ideally before they occur. And just a little snippet from the paper, considering that mining activities can have impacts that are long-lasting, spatially extensive, and costly to mitigate, there is a clear need to effectively link science and the science around these practices or these processes and the known complexity of mining impacts to risk assessment and decision making. So Chris, feel free to add to my brief introduction during our hour together. And with that, I'll turn the mic over to you.
Thank you, Nick. Let me get my title slide up here for everybody. Get this full screen. Is that looking full screen, Nick?
There it is. Yeah, it looks great.
Okay, great. Thank you very much. Thank you for the really nice intro. I really appreciate the opportunity to present today. This is whoops, I'm at the end of my talk. Wow, I really got through. See you later, everybody.
Let's go straight to questions.
Let's go to the title slide. There we go. Thanks again. And as Nick said, yeah, I spent 10 years in Juneau from 2011 to 2020 in Tlingit territory. And it was just really, I can't say how much it had a huge influence on the way I look at my perspectives on life and science, and really reinforcing the value of clean water and healthy fish populations that people depend on. Those were really formative years for me, and I appreciate that time. Now I work remotely for the Flathead Lake Biostation and live in Seattle, Washington. In Coast Salish territory, I grew up in this region, in the kind of back in the place I grew up. So happy to present today, and I hope I can make it interesting and worth your time. Just situate myself a little bit here. So I want to start by describing the place I often think about when I think about mining in rivers, the Tulsa River, which is in far northern British Columbia on the lands of the Taku River Tlingit. It's a large tributary to the Taku River, which flows across the political boundaries from BC into Alaska near Juneau. On the right side of this recent photo, this red building here is where Tulsa Chief Mine sits. It's been leaking acidic and metal-laden waters into the Tulsa River since the 1950s, and it's just now in line for remediation. Where I'm standing, it's late summer, and brown water with about 3 inches of visibility is flowing by. The water has that, for you that are familiar with glacial rivers, which I'm sure is a lot of you, the water has that subtle hissing sound to it, thanks to the glacier sediments in it. And even though it's summer, the water temperature is barely above freezing, thanks to the large ice field that's providing most of the runoff you see here. The rocks around me are large and loose and signal that the river channel is active and moves around frequently. Part of the reason this river is so active is because it originates here in the Juneau ice field, which supplies a massive amount of water to the watershed during the spring and summer meltwater periods. These meltwaters can sometimes burst into the river in pretty dramatic fashion. So if you head downslope from here in the ice field and follow the Tulsa Glacier, you end up here at the headwaters of the Tulsa River. We're now looking upstream at the toe of the Tulsa Glacier. Can people see my mouse, Nick? Can you see my mouse? Okay, great, thanks. And so we're here at the headwaters looking at the toe of the Tulsa Glacier. And during the spring melt, large lakes form in valleys above the toe of the glacier up in this section up here. And when the pressure from the growing lakes becomes strong enough, these waters burst out from tunnels under the glacier and create massive floods spreading across the floodplain and often rearranging the river channel. So I want to show you, and I hope this works. I hope we have the bandwidth for it to be relatively smooth. I want to show a 1-minute video of what one of these glacier dammed lake valleys looks like. In the video, we're going to be flying up the Tulsa Glacier here and turning right into a basin right over this ridge here called Lake No Lake. So here we are flying over at Tulsa Glacier, and we're about to drop down into the dammed lake valley. You see where you kind of go from that really hard, stable glacier ice down into this kind of dirtier, more broken up ice. Those are icebergs that were previously floating a few months before this video into a giant lake called Lake No Lake, which really holds a large volume of water. So we're dipping down into that lake valley, and we're going to turn right. And it's really hard to describe the scale of this valley. Some of these chunks of ice that will be above our heads when we drop down are a few hundred feet above us. It's a really, really big, kind of scary place in a way if you imagine yourself down there. And as we turn right, you'll see this very large cavern here in the bottom right corner. That's where when the lake builds up enough pressure, it bursts through this year. And that's where the floodwaters come out in the Tulsa River floodplain. So you've got all these icebergs sitting on the valley bed here, and you're just surrounded by this very, very powerful place. And this is the origin of these glacier outburst floods. If you saw a bear down here, it'd be really, really hard to see. Very, very large scale. So I hope that came through for most of you and you were able to see some of that. The question is, why am I taking the time to tell you this? And why does this environmental context matter in relation to mining? In Western North America, and especially Alaska, it's at the front lines of climate change, where we expect to see continued glacier retreat, warming air temperatures, less precipitation falling as snow, and more frequent flooding and drought. The steep mountainous and extremely wet environments in some places throughout this region also push the limits of engineering needed for large mining projects. Things like landslides, glacier outburst floods like I described, large permafrost thaw slumps. These are all expected to become more common in the future. In the work I'm summarizing today, our paper looked at the region starting in the Columbia Basin in the south and worked its way through British Columbia and the Yukon and the state of Alaska all the way up through the Arctic. And throughout this region, there's a lot of historical, currently operating and proposed mines in North America, northwestern region of North America. The teal circles on this map of the region show the largest 26 coal and metal mines currently operating. The size of the circle is based on the average amount of ore. That's the economically valuable rock as a product of interest such as gold or copper. That's processed in metric tons per day. I think this map does a nice job showing that large mine projects are spread throughout the region, from the Columbia Basin through the Arctic, and especially throughout British Columbia, and watersheds shared with southern coastal Alaska. What it doesn't show is that there are also dozens of other large projects proposed or near the beginning of operations. So northwestern North America really does represent a part of the earth where extensive mining pressures overlap with some of the best remaining rivers and healthiest salmon, trout, and char populations. In this presentation, I mainly concentrate on large metal and coal mining operations because they tend to be the largest current and proposed operations in the region. Although there are other operation types that are things like phosphate, sand and gravel, or graphite that have important impacts to consider as well. My goal today is to hopefully bring a greater appreciation for the current overlap between proposed and operating mine projects and salmon-bearing watersheds in this region. And I'd like to briefly discuss some basic aspects of mining operations. Also briefly discuss some of the pathways of mining impacts to fish, and end by outlining some key scientific questions intended to promote transparent discussions of whether impact assessment processes are sufficiently considering mining risk and uncertainty. Many aspects of this paper from this presentation stem from a paper that was published a few months ago in Science Advances. It's freely available online. I think the announcement for the webinar provided a link. I want to acknowledge the contributions of the 22 other co-authors that represent an incredible mix of science and policy expertise, especially Aaron Sexton and John Moore, who made major contributions to the content and organization of the paper. I also want to acknowledge Wilberforce and the Salmon Science Network, who helped fund the initial workshop that kicked off this effort. And I'd like to personally thank the Taku River Tlingit First Nation, both the staff and community members, whom I've been lucky enough to work alongside over the past 4 years in the Taku River watershed, and where I've been provided a lot of the experiences I share here. So why are mining and salmon a pressing issue, especially in a place like Alaska? Many news articles you've probably seen out recently have talked about the Biden administration's funding of domestic mining to satisfy the emerging supply chain for metals and other minerals that support electric vehicles and other green infrastructure, wind turbines, things like that. At the same time, while many healthy salmon populations do remain in Alaska, we also all know that some populations are showing signs of decline in places where they were previously abundant. In some places, increased mining operations will overlap with these watersheds, and there's a need to look at these overlaps closely. So let's dive in. What do salmon need in freshwater? This is a really fish-savvy group, so I'm just going to take one slide just to briefly kind of remind us all of some of the things. Salmon are well adapted to their home lakes and rivers. They often cue their life history and timing of things like spawning in eggs and incubation to natural patterns of stream flow and water temperature. They also need clean water that's made free of major pollution. And really importantly, especially when you see things like Bristol Bay and places where sockeye salmon are extremely important, they have access to really diverse and intact habitat, things like clear water tributaries, large main stem rivers, and side channels and wetlands fed by groundwater. These places all react differently to different atmospheric conditions and floods and droughts, and provide fish what they need to thrive within that watershed. So what risks does mining pose to these kinds of habitat needs? I modified the primary conceptual figure from our paper to help lay out the next part of this talk. I want to very briefly describe some of the key features of mining operations and the potential harm they can impose on watersheds. Overall, I hope to convey how the ecological complexity of rivers and their watersheds, especially in this era of rapid climate change, creates risks for mining projects that can sometimes be hard to mitigate or avoid, and at a minimum should be considered carefully before new projects begin or existing projects expand. When we're talking about large mining projects for metals like gold and copper, there's kind of two broad categories of operations: open pit and underground. Underground mining creates a system of tunnels and underground rooms from which to extract ore. These mines tend to have a smaller footprint above ground and produce less waste rock than surface methods, but they can also have their issues like sinkholes and land subsidence, and they definitely have water management issues, especially for a technique called block caving, where massive amounts of earth are removed underground and is a little different from traditional underground mining. Open pit designs use blasting and earth moving equipment to excavate terrace depressions tens to hundreds of meters deep, usually requiring commensurate water table drawdown and groundwater management. These mines tend to exploit lower grade ore deposits and therefore need to remove much more earth to extract the metal of interest. Since many of the high grade deposits in this region have already been discovered and exploited, there's a larger number of proposed open pit mine designs these days. Here's the infrastructure associated with Red Chris Mine, which is located in the headwaters of the Stikine River. In addition to the open pit on the left, we can also see the tailings reservoir on the right, which can be present in underground and surface operations. It's often the most conspicuous component of a mine's footprint. The concentrate produced by the grinding and chemical treatment of ore leaves a slurry of liquid and fine solids called tailings. Wet tailings are usually stored in impoundment facilities contained by embankment dams, like the ones at Red Chris Mine pictured here. Less commonly, tailings are dewatered, filtered, and stored in an unsaturated form in engineered piles called dry stacks. Dry stacks are touted as a lower impact and safer form of storing mine waste. But over the past 4 decades, only 3 to 6% of new tailings facilities globally use this technology, which tends to be more expensive and sometimes complicated to implement. I think it's important to define what I mean when I say low-grade ore. A common low-grade, and they vary of course, but a common low-grade you'll see is getting 0.5 grams, about 0.02 ounces of gold per metric ton of rock, which is about 2,200 pounds. And that's what about this 20-foot fishing boat weighs. Now in my wedding ring, there's a little over 5 grams of gold. So at that grade, it would take well over 20,000 pounds of earth to be moved and processed to get the gold in my wedding ring. Since many of the proposed mines in this region we're talking about today are likely to use open pit methods, I think it's important to recognize this ecological trade-off and the amount of earth moved in the land and water connections that are reshaped forever in these kind of operations. One of the ways mines impact salmons is through altered hydrology and temperature. Salmon, trout, and char, like I mentioned earlier, have evolved to match migration, spawning, and egg hatch timings with environmental cues that are in large part driven by patterns in stream flow and water temperature. At the same time, mining uses water intensively for many different uses, including processing ore, covering up acid-generating tailings, and controlling dust on site. Open pits often fill with groundwater and can interrupt surface water, groundwater connections in the watershed, which is critically important to cold water fish populations because groundwater inputs serve an important role. They tend to cool waters in the summer, and they tend to provide warm, non-freezing water that can be used for rearing during the wintertime. Considering the importance of water for mining operations and also for fish, it's really important to understand how each project alters the hydrology and water temperature of the watershed it lies within. Salmon, trout, and char are famous for living in any size waters, from tiny headwaters to big rivers and migrating all places in between. Therefore, developing infrastructure within a watershed very often directly takes away habitat for salmonids. Tailing storage reservoirs are one of the most obvious pieces of mining infrastructure, leading to habitat modification and loss. In contrast to more conventional water storage dams, which are licensed and built for a finite operating life, tailings dams must hold back their slurry essentially forever. The likelihood of leaks or dam failure compounds over this multi-generational time period as facilities age and projects no longer generate revenue. In southern British Columbia, when Mount Poly Dam failed in 2014, 9.2 kilometers, Hazeltine Creek, which is known as valuable salmon spawning habitat in the upper Fraser River watershed was buried in tailings. The tailings dam for Red Chris shown in the previous slide is about 3 times higher, holds much more tailings volumes, and was built in a similar manner to Mount Polly. Even though these tailings from Mount Polly fell to the bottom of the 3rd deepest lake in North America, Quesnel Lake, brand new research out just a couple of weeks ago has found that the lake turnover in the fall, when the bottom and surface layers of the lake mix, resuspends contaminated sediments, and these flush downstream into the Quesnel River. The tailings don't just sit quietly on the bottom. And in this case, dilution did not solve the problem for this disaster. In addition to tailing spills and leakage, other forms of pollution from mining can directly compromise the health of salmonids. One well-known source of pollution is acid mine drainage, where sulfur-bearing minerals, which were previously buried deep in the earth, are extracted from the ground and then react with water and air to create acidic runoff. This acidic water dissolves trace metals and causes them to be transported downstream. That is happening in the orange water you see on the left leaking from Tulsa Chief Mine. Not all pollution is driven by acid mine drainage. Another well-known source, for example, is selenium leaching from waste rock piles of coal mining operations. High levels of this of selenium can result in fish deformities such as missing gill plates and curved spines. This type of pollution is seen downstream of the massive Teck coal mining complex sitting within the Elk River watershed of southern BC, which is a tributary to the Kootenai River and part of the larger Columbia River Basin. Elevated selenium concentrations attributable to this mining complex have been measured tens to hundreds of kilometers downstream. So I think the most basic and important take-home message here is that the effects of mining can be long-lasting and spatially extensive, lasting decades or even centuries for cases that have been documented in Europe, and spanning hundreds of kilometers downstream in some instances. So this is just a brief discussion of some of the pathways of mining impacts on watersheds and salmon within them. In our paper, you can read more about additional impacts listed in this figure and specific places where these impacts have been documented. In fact, we can list a lot of different documented impacts from mining operations, but this discussion of mining impacts really brings up to me what's the most critical question. Is harm from mining common or rare? When our group first set out to write this review paper that I showed earlier, we wanted to tackle this question head on by systematically comparing the impacts predicted during impact assessment processes, such as in environmental impact statements in the US, versus the observed impacts during the life of mine operation. But what we found was that data and transparency needed to do that robust analysis of before and after predicted impacts wasn't available. The data and transparency we needed wasn't there. In fact, we found only one study in North America that attempted to do this by looking at water quality predictions before and after mine operations. And they found that in that work, which included a lot of mines in drier places like Nevada, Colorado, Wyoming, they found that 16 of 25 mines exhibited worse water quality than predicted during the environmental impact statement process. They conclude that similar studies have not occurred for several reasons. Data might be unavailable or proprietary. Data that have been collected for a long time might be spread across multiple microfiche digital and paper repositories, making it really hard to put these things together. And maybe most importantly, the time, space, and method replication needed to make comparisons across years is often insufficient. Either methods change, the places that were measured change, or there aren't enough measurements in really dynamic places like rivers. So therefore, based on what we learned there, we pivoted our objectives and came from an angle of knowing that some mines do harm, but it's also likely that some do operate better than others. And to recognize this fact, and in light of a before and after analysis of impacts, we outlined 4 key scientific questions intended to promote a transparent discussion whether impact assessment processes are sufficiently considering risk for a given project or group of projects. These are the questions. Number 1, to what extent is stressor complexity acknowledged or analyzed? For example, what we mean here is that most water quality regulations are based on single metal thresholds, like mercury may not be above a level or copper may not be above this level. But research has shown that multiple metals in the same water existing at high concentrations can combine not just in a straight additive manner, but sometimes synergistically to create stronger impacts on aquatic organisms than would be expected. And this is not well represented in current regulations across jurisdictions throughout the region. Second question is, are cumulative effects sufficiently inventoried and quantified? I have some extra slides on these next few questions. Are long-term mitigation strategies based on proven technology and robust to future change? And are climate change risks incorporated into impact assessment and mitigation strategies? The term cumulative effects refers to the combined impacts of historical, current, and future human activities in some defined area and time frame. It can refer to mining, forestry, hydropower, etc., many other things. One of the things that struck me while originally pursuing this work and research was the high modern day density of mining claims in some regions, especially in the transboundary region, where watersheds cross the political boundaries of Alaska and British Columbia. This area is known in the mining industry as the Golden Triangle. This is the Taku, Stikine, and Unic rivers, which is really the small green watershed here. And these black polygons throughout, those are individual mining claims. In BC, it's possible to stake a mining claim using an online portal and paying a nominal fee from your desk. In this map of the three key transboundary watersheds I work on commonly, 19% of the watershed area is staked. And this floats over time. Sometimes these claims change from year to year, but this is basically the lay of the landscape here. 59% of the Unic River watershed and the entire Iskut River corridor here, the largest tributary to the Stikine, is staked. So Mine Corporation will point out that just because land is staked doesn't necessarily mean it will convert to a real project. And that's true. But for regular people like me who are outside these corporations, how do we know what lands are most at risk for development in the future? Also, the vast staking that you see in maps like this implies that all of these watersheds will be exposed to mining impacts of some level at some point. So in this transboundary situation, heavy staking is also at odds with other values in the watershed. These rivers flow from Canada into US National Forest Service wilderness lands, which are the highest form of land protection in the US. So I tend to get a lot of questions in presentations like this about specific mining projects. And because it's such a large region, sometimes I know about particular ones and sometimes I don't. So in lieu of knowing a lot about individual projects that you might all be concerned with, I thought I'd provide some of the key questions that can be asked when community members are reviewing potential impacts of a mine or participating in that review process. So around cumulative effects, I'll just read these. I think they're really key things to ask in some form or another. What other mines are proposed in this watershed or surrounding area? If this mine is built, what other mines or development activities will still be allowed within the same watershed afterwards? I understand that many mines expand beyond their originally proposed footprint and scale of operations. What are the chances that this mine we're talking about will expand in the future, and what processes govern that expansion? Will I have the same opportunities to comment on that expansion? I think those are key questions we can all ask when we're thinking about the impacts of mines. Another one of our questions around science and mine governance was, are long-term impact mitigation strategies based on proven technology and robust to future change? In one example, unexpectedly large precipitation events have challenged the water storage and treatment facilities of the Minto mine in the Yukon watershed and led to discharge of untreated mine water during salmon runs. A couple of years ago, unexpected permafrost thaw at the Red Dog mine in Arctic Alaska led to poorer than expected water quality and overwhelmed the water treatment system, forcing open pits to begin filling with water while the mine troubleshooted the problem. We point out several more modern examples such as this in our review paper, but I think the important take-home message here is that despite improvements to modern day mine assessments and engineering, these problems are still occurring. And they will be harder and harder to engineer our way out of because things like the magnitude and frequency of extreme floods and drought are becoming impossible to predict accurately under a rapidly changing climate. Here's some good questions to ask about mitigation strategies. I understand that climate change is making it hard to accurately estimate future frequency and magnitude of floods and droughts. How have engineers designed the infrastructure for these projects to account for these uncertainties? And also, do any successful examples of the proposed water treatment process or any other kind of mine feature that's being designed currently exist at the same scale proposed here? In other words, is the technology for a proposed mine something brand new that's never been tried before, or is it tried and true? There's another reason to be forward-looking when we talk about new mines being proposed. A recent, I think, really cool study showed that glacier retreat will open up thousands of kilometers of new salmon habitat over the remainder of the century in the mountain regions in northwestern North America. We might think of this in some ways as a silver lining for climate change. At the same time, it's also important to consider that mines may compromise the viability of habitat that is maybe not important for salmon now, but will be in the future. This is not currently accounted for, to my knowledge, in mine governance. It's happening very quickly in some places. Here, we are back at the river, at Tulsa River, where I started. This emerging lake, called a proglacial lake, is new salmon habitat forming before our eyes just in the last 20 years. This providing salmon with a new refuge that didn't previously exist. At the same time, mining companies also look at glacial retreat as a new opportunity to find undiscovered deposits. So there's a need, again, talking about this overlap between mining and salmon, a need to develop forward-looking policies in northern regions about how to resolve this tension between protecting future salmon habitat and glacier-covered watersheds, where glacier retreat is presenting potentially new mining opportunities. So I'm on the last slide, and I really appreciate that everyone stuck with me through a pretty broad and I think fast overview of a lot of different topics related to salmon and mining. I really want to stress that the point of my presentation is not to be anti-mining. I want people that live in places affected by mining to know the risks and environmental trade-offs. If there's one thing I can pass on to people about the effects of mining, it's to know that the decision to allow a mine to move forward with operations is a big one. Once a large mine is in place, the landscape is permanently transformed for decades to maybe even centuries. So to make these decisions as a society, we need the best possible information, good science, and open, transparent governance process. There's my email. I'm happy to take questions later you might think of, and it sounds like we've got a few minutes to hang out and chat now. Thank you.
Thanks so much for that presentation, and yeah, for sharing your contact info. And yeah, I hope people reach out to you in the future with ideas and questions. It's wonderful resources. I really appreciated the question format you shared. Those two, get the brain thinking about these issues, and looks really useful. There's one question here in the chat from Jones Hotch saying, I'm wondering what more we can do besides water testing. So if that, I guess if there's other ways to be monitoring these systems that might be able to be put in place.
Yeah, I think there's a lot of new, typically in ecological monitoring, there's several things that are done pretty regularly. Sediment is monitored for metals often because it'll have different trends from water. I think what the question might be getting is that water flows through fast, it's very transient. Pollution can pass by, you can miss those measurements. And there's other ecological measurements you can make that are more representative of long-term pollution. So sediment, aquatic macroinvertebrate communities, the bugs living in the rocks, sampling the diversity and abundance of those is a really great indicator. Something kind of new I'm learning about in glacial rivers, it'd be really cool to get the chemistry of the tissue of those bugs to see how their exposure is increased or not in metals. That's really easy to do with fish. Usually they're big enough that you get enough tissue that you can do a lab analysis of fish. With bugs, usually sometimes there's not enough to get like the 10 grams you need. But I've just learned about new techniques. There's this laser ablation technique where you can take 1 or 2 individuals and actually measure the metals off of them. So I think there's a lot of really promising techniques beyond just water testing that are already in use and coming online.
Thanks. Yeah, one of our guests mentions that water quality must go side by side or hand in hand with other monitoring like sediment sampling and aquatic monitoring. So, yeah, I'm trying to imagine what 10 grams of aquatic insects looks like. It may be quite a large pile. Yeah, it's a big pile. Maddie Halloran is chiming in here. It seems like there is a spectrum of impacts from the different mining techniques. Is open pit mining used so frequently because it is the cheapest or easiest, or is that the only way to access minerals in low-grade deposits? And she asked a follow-up question as well, that if an open pit mine is proposed, is it even feasible to advocate for a different design?
I think I know the answer to part of that, which is, my knowledge, yes, open pits are conventional and cheap and give some of the best economics for profiting from the mine. So I understand that there's technological advances in mining that could reduce the impacts of open pit mines. I'm not familiar enough with the specific engineering for how feasible a lot of those are. I would say that one thing that is very reasonable to request is to see if people are open to dry stack tailings management over wet tailings management, so you can reduce the need for an embankment dam that holds back wet tailings. I think that's an important ask to make. But yeah, I hope with all the needs for minerals and metals coming up that we are going to be forward-looking and innovative and come up with new techniques that have less impact than some of the more traditional techniques.
Thanks, Chris. Here's another question for you. What methods can we use to identify future salmonid habitat? So they say today's protections are based on actual use by actual critters. How can we predict future use in ways that will stand up to likely challenges by mine proponents?
Yeah, that's a great question. So that paper I presented by Kara Pittman and others, what they did was they used a digital elevation model of all these watersheds where glaciers currently sit on top. They use glacier retreat predictions to look at the speed of retreat. And then they highlighted all the future river channels that are less than 10 or 15% channel gradient. And they assumed that those would be accessible. So, and also I should say the ones that were downstream of that already accessible to salmon. So then they extrapolated up those river channels to, there's a map available through that paper showing where that new habitat lies. And of course, there's uncertainty with that, like any kind of prediction, but it's the best thing out there so far to predict where this new habitat will come from. And that can be downscaled into any watershed where there's a glacier that took place in the study region.
Yeah, that does sound like an interesting paper. I'll see if I can track that down from your slide.
Great. I think that is an open access one as well, but if it's not, let me know and I can send it over. Thanks.
Yeah, I'd like to have a look at that myself. That's quite an interesting thought exercise. And it sounds like it's going to be the future. The future keeps coming. It's unavoidable. There's a question here from Katie Singer. They write, what the metals we mine to go to manufacturing computers, solar, wind, electric vehicles, etc. Is there any discussion about limits to mining, limits to growth, repurposing what we have, and drastically reducing our mining and consumption?
I think that's a super key question. I think about that kind of stuff myself. I know there's a lot of people working on that kind of supply chain issue. My understanding is that we can't totally get there for what we need for green infrastructure with just recycling. Mining is necessary, but I also think it's a dynamic target because, again, a little bit outside my expertise, but I just read the other day that lithium batteries are even being innovated already where they don't need lithium anymore, like things like Tesla are using different, less intensive forms of metal harvesting to make new batteries. So I don't know a lot about it, but there is going to be some mix of recycling and mining, and I hope we are doing our best as a society to recycle absolutely everything we take out of the earth.
Another question here from Ted Shetler about that. You mentioned dry stacking. Do dry stack tailings need to be protected from rain and snow to prevent leaching, or maybe some sort of underground barrier? If so, does this protection not need to be permanent?
Yeah, I'm trying to think. So, in Alaska, Greens Creek mine has dry stack tailings. And I believe the way that one works is they have kind of a lip embankment of earth around the dry stacks. There's a liner underneath the stacks, and it's also covered to protect it from those issues you mentioned. And I think it's a really good question about, yes, those do need to be covered forever, essentially. And I don't know how well that works. I don't know examples off the top of my head for like what's the longest period of time a dry stack has been kind of covered and protected and how well that worked. But I think that's an important issue. How, once the mine is over and stops generating revenue, how do you keep those things safe and tidy?
Thanks. Yeah. It does sound like a, what was the name of the mine in Alaska?
Greens Creek mine near
Greens.
Mm-hmm. It's on the island.
Here's a question from Dan Cannon. Well, thanks. He says, Chris, thanks for the presentation. And how can the public hold the mining industry's studies, data, reports accountable? Often findings and data is given to the public, and the public doesn't have the expertise to question the results. And he goes on, is the scientific community pushing these corporate studies, data reports to be peer reviewed? And what does that process look like? Yeah,
that's great. Thanks, Dan. It's definitely a long game, right? Like these, environmental, for anybody who's cracked open an environmental impact statement, they're hundreds or thousands, probably more on the thousands of pages level. And how does any one individual, even a technically savvy person, review all these things? So, I personally know scientists pushing for these kind of things, better transparency, better data. I've personally helped with reviewing individual mine proposals and commenting on those for communities that are interested in exploring the impacts. You want to tell people to participate in the public process, but again, if that process lasts 10 years and there's 6 or 8 meetings a year, like, can you really expect people to stick through it? So it's kind of a village effort, we all, if we're concerned about these things, we all need to do our part to pitch in and not to be overly kind of Pollyanna about it, but I just think it's really important for all of us to work together on that. And I know I certainly will be pushing for this better data transparency. And I think mining doesn't get as much exposure as other kind of things, at least further south, where I'm familiar with, forestry, hydropower, these things get a lot more lights shown on them. So I think mining, because of its importance in the future, has become more and more important. And I hope, it's kind of a rambling answer, but I hope that results in people putting more effort into reviewing these and working together to create less impacts. I hope that made sense.
Yeah, thanks, Chris. There's another question specifically about for Canada. When mines are proposed in British Columbia, Canada, is there a process like in the US, environmental impact statements for comments?
Yes, there's they call it the environmental assessment process. It can be run federally, provincially, or combined between the two. It has parallels to the US, but some differences as well. There's some good papers. If anybody really is interested in that, email me and I can pass on some things about Canadian environmental assessment.
Perfect. Adam writes, are climate change threats included into mitigation strategies these days?
That's a hard one. It's a very good question. I think it differs from project to project. In some ways they are, when depending on how, one thing that's often calculated is the probable maximum flood, right? Like how much water could possibly dump into a tailings reservoir. And based on that, how big does the dam have to be to make sure it's all held back? What kind of spillway needs to be on it? Things like that. Those tend to take into account climate change, but the problem I point out in a lot of those calculations is, scientists call it stationary versus non-stationary calculations. So stationary means that you can calculate the mean of extreme precipitation events for the past 30 years. You get some variability around the average and say, oh, well, they get this big or this little, and that's how we'll design it in the future. But now with climate change, things are non-stationary, which means that average from 30 years past is fairly meaningless. And we're busting records. I mean, anybody who lives in Alaska knows we're busting records all the time, right? And here in Washington, same thing. Driest month, wettest month, hottest month. And that's really challenging those kind of engineering calculations. And I don't think that's an open and transparent discussion at this point.
Here's another question about dry stacks. Do you know of any proposals to turn existing tailings ponds into dry stacks?
Oh, wow, interesting. No, I don't off the top of my head is the short answer. I think there's several mines proposed in BC where they're debating right now to go with wet or dry, but they haven't decided either way. That's a good question. I'm not sure.
Sumaga writes here, do you think scientists know enough about the risks of mining in Alaska to develop Alaskanized best management practices that can give communities and agencies a benchmark to push for?
Good question, Sue. I think so. It would be fun to dive into that question with you. My reaction, though, in the back of my head when I heard that question was, because we have so many watersheds like the Yukon and the Stikine and the Alsek that are shared between the Yukon and BC and Alaska, I would love to see more harmonized guidance that is cross-jurisdictional. And I think there's enough to know about that, or at a minimum, let's point out the information gaps as we make that kind of document. So let's do it, Sue.
Representative Jesse Keel is here, is sharing with us here that his understanding Greens Creek has posted actual cash in the low 9 figures to deal with runoff from the dry stack for decades after closure. So that's just to add to that. I'm certainly intrigued in knowing a little bit more about that example. Like you said, it's good to have examples where they're actually doing it and learning for those if you want to suggest it as an alternative to existing tailings piles. Allison Kelly asks, can you repeat the basic topic of the paper regarding upstream tributaries or the author?
For the new salmon habitat?
I think so.
Let me just scroll back to that. There it is. So that's in a journal called Nature Communications. I'm pretty sure all Nature Communications articles are open access. So if you put that title into Google, it should show up and you should be able to download the PDF or view the website.
Great. I'm just saying, Sue writes back, let's do it, Chris. So you've got it.
Thanks, Sue.
Yeah. Hal Shepard, thanks very much for the presentation. The Norton Bay Intertribal Watershed Council, along with tribes in the area, have been monitoring a large graphite mine proposed for the highly productive Emmerich Basin of Alaska. They asked, can we get permission to post this presentation on our website or otherwise reproduce it to help get the word out about the potential impacts of this and other mines in the area? What do you think,
Yes.
Chris?
Absolutely, yes. Thanks for asking. Sure.
Yeah, I'll share a link to the recording in an email that'll go out to just anyone who's registered later today or early tomorrow. And yeah, we keep a database of all the recordings on Alaska Community Action on Toxic's website, at least all the ones that we have recorded. So yeah, I encourage you to share it. Let's see. Well, yeah, if anyone else has any final thoughts, we are kind of nearing the end of the hour. Chris, do you have any final thoughts? Think ideas or something that's come up that you'd like to leave the audience with?
Yeah, I tried to express this whole, like, the decision's a big one, to make a mine. That's just the main point I've told reporters and other people in presentations, is that, like, consider it carefully. Like I said, I'm not anti-mining, but I think we need to do a really good job choosing where these things go and how they operate. And, I'm with everyone there trying to be involved and review these things. I sympathize with you, and I know it's hard, and thank you for your work on that. And I really appreciate, again, Nick, the invite. So thank you very much for giving me the opportunity.
Yeah, it really is our pleasure. Jen Woolworth is asking, are we seeing an increase in mine tailings dam failures due to changing climate?
Oh, I don't know if there's definitive data on that. And I wish I could remember the statistic off the top of my head. There is a report. If you want to email me, remind me and I can send it to you, but it's something like, I think it was done for Canada. They expect 2 tailings dam failures a decade. It was a report done by folks a few years back now. And then there's also a global analysis of tailings failures I can share, and I can't remember the rate. I don't know that anyone's shown evidence of it increasing recently, but I would certainly expect that as something to be worried about.
That makes sense. But yeah, I'm glad those studies exist. Well, like I said, I'll put together an email and send it out, hopefully later today, with a link to the recording for this. And I encourage folks to share it with others who weren't able to join us this morning. Yeah, it's useful stuff. Our next Che Alaska webinar will be on Wednesday, November 16th, when we'll be joined by 2 staff from the organization Earth Justice for a presentation on ongoing legal pressure on the Food and Drug Administration to restrict the use of phthalates as food additives and in food packaging. We're going to pack the last 2 webinars of the year here on sort of slightly off dates, but so November 16th we'll be speaking on phthalates, and then we have the final Che Alaska for the year scheduled for November 30th, and that will be with Dr. Laura Anderko, who will be sharing recommendations for clinicians on the potential health effects that may be associated with exposure to PFAS or per and polyfluoroalkyl substances. And Dr. Anderko has recommendations for best practices and principles to be used by clinicians in their decision-making process, especially when there's uncertainty in outcomes in the scientific literature. So that promises to be an interesting one as well. And thanks again to everyone. Thanks to Chris for joining us and for that excellent presentation. I definitely know I'll be tuning back into that one once or twice to check on that great info. There's a lot of thanks coming to you in the chat. And
thank you, everyone.
I hope folks are able to get your email from the slides and reach out to you with future questions.
Yeah, don't hesitate, folks. I have to get emails. Thanks.
Perfect. Well, yeah, thanks everyone. And till next time, have a great rest of the week.
Bye.